Hi everyone, I'm Samuel Yvon. I'm an undergrad student at the University of Montreal and I work with Professor Mark Feely in the Programming Language Lab. So today I have the chance to present to you a Scheme operating system which is effectively running Scheme on bare metal. And I've been working on this project for the past year or so and I'd like to maybe give you an overview of what it is in making a system like that. So you might as well be wondering what the Scheme on bare metal really means. And we wanted to explore the idea of having a language runtime as an operating system, meaning that the language runtime will access all the hardware and provide drivers over the hardware. Of course, all the language features that are normally available will also be available within what you would call the code that interfaces the hardware, so the drivers really. What are traditional applications will just simply be modules running in their own thread of execution. And a good question to ask is, do we gain something by doing this kind of design? And if so, what do we gain? Immediately, you can observe that many operating system services are duplicated within a runtime. So for instance, an operating system has an implementation of threads, but also many language runtime have their own implementation of threads. So already there, you have less duplication of the same operating system services. Safety mechanisms that are baked in the language will also supersede some operating system level security that might not be needed in a safe language. For instance, with Scheme, you don't have a danger of doing invalid memory operations. And maybe as a final argument for why you also gain other things is that, and it's in the same vein as the last point, but you have high-level features that are not typically afforded in an operating system kernel that you can now use to your benefit and to increase development speed. So this idea really works with any kind of language. But here we show Scheme because it gives us a good level of performance and many features that are going to help us into achieving our goals. So maybe the main feature that we are looking forward to use is the fully featured rich REPL experience that is given to us by a Scheme runtime, and in particular the Gambit runtime. So this is the one we used. With Scheme also gives us fully featured threading primitives. So we have threads, mailboxes, and many tools that are going to help us doing code without really multi-threaded code without really having to worry too much about synchronization, because the tools already include many of the synchronization requirements. Garbage collection is also given to us by the language runtime, but it is common to many runtimes, so this is not very much a Scheme only thing. And maybe another great point is the fact that Scheme is a very dynamic and malleable language. So if you want to extend it to do things that it's not really meant to do, which is exactly what we're doing here, the Scheme language has many tools to help you achieve that, and it's really helpful. So maybe before going into too much detail, let's switch over to a little demonstration. Oh, there we go. So this is the operating system that is booted within QEMU. So just to see that everything works, let's do a little bit of arithmetics and just compute a big number. And you see right here that we have big num support and everything works as you expect. Maybe to learn a little bit more about what's running inside the system, we'll look at the running threads. I'd like to point your attention to the notification pump thread, because we'll talk about that one later on, and the UART REPL, because we'll use it in a second. The UART REPL is a REPL that is accessible through a serial connection, so you can do remote development on the system. But before we switch that, one recurring need in operating system is the ability to read and write to arbitrary memory location. And as you may know, this is not something that's usually found in Scheme implementation, but for our needs, we have it here. So just as an example, we'll go read the bootloader, and we call our system Mimosa. So in the bootloader, we should find the Mimosa byte string at the beginning. So if you remember, the bootloader is at this location. What we'll do is that we'll just simply read over that location. Address fetch 8. False is a null pointer, so we start from the 0 location. This is a kind of a magic value. Bootloader start, and we add 3 because the byte string that contains Mimosa is at an offset 3. The first 3 bytes are the jump instruction to jump to the bootloader code. And I read 3 bytes. I need to read 8 bytes. So this is unfortunate. We'll just switch over to numbers, to characters, sorry. Well, now we can just do a simple map here to character L. And we have the Mimosa boot string, so we are in the correct system. I quickly mentioned earlier the serial REPL, so I'll switch to that. There we go. clear everything. So we can just connect by using telnet localhost 44555 because this is, like I said, this is an emulated machine. So we can just connect to it. And just to make sure that we are in a scheme REPL, we'll just type a form. There we go. One thing that's one recurring need in an operating system is the access to files. Just to show that we have access to files in our system, we're just going to go read the root directory of our system. So because we re-implemented the file system access in Scheme, we don't have access to the traditional Scheme IO function. So we have our own implementation, but we could bind the traditional function to these. But it's a good example, I find, to use our own function to show what we're really doing here. The fs variable is the current file system, the one that the system is booted on. So we see that we have the boot.sys file, which is the kernel, and we also have conveniently an ICFP 2020 file. So just because it begs us to open it, let's do exactly that. So the user load is equivalent to the scheme load function, just load a file in memory and put it in a current execution context. There we go. So we have the sum function, and what the sum function will do is that it will just compute the sum from 0 to n, and s is just a counter to do a tail recursion. So it'll show that tail recursion is also working properly in our system. So we'll just put a big number and put 0 and wait for that to compute. There we go. So that obviously would not have worked without tail recursion. We would have destroyed the stack. So you see that we have full scheme support in our system. So maybe to as a little overview, if you want, before diving deeper into the more important part of this presentation, I'd like to maybe talk about what we can do in our system from a more theoretical standpoint. There we go. So our system is based on the Gambit runtime, and it's an x86 32-bit operating system that's built for the Intel platform. It runs on real and virtualized hardware. For the need of this presentation, this is on QEMU. And like we wanted, we have full REPL support, so we can use the REPL to do the operating system development without any issue. We also have a variety of drivers that we consider to be a minimal subset of really what's interesting for this experiment to be telling us something. So we have the keyboard driver that is in Scheme, as well as the UART, which is the chip for the serial driver. We have training support, of course, given to us by the Gambit runtime, and we have IDE and FAT32 to read the hard disks. We also have a clock driver for the real-time clock, which is really standard stuff. And we also have, of course, as you saw, a video driver to display things on the screen and a terminal access, but those two drivers are in C because what we did is that we took a small operating system that was made for teaching OS basics and we rewrote it gradually in Scheme. So in order to bootstrap everything successfully, we kept the video and terminal in C so we could see that our development was working properly. But at this point, and as far as the project is right now, there's no reason why it's not fully ported yet, beside time. So it is a work in progress. And of course, by using the Gambit runtime, we gain many interesting features. So we have on-the-fly code generation, garbage collection, of course, and we can interface with C through the foreign function interface, which we can use to extend the language a lot. So, for instance, the fetch-u8 function that I use is not a traditional Scheme function, so it is implemented with a C lambda that just embeds C code within the Scheme function, and it's a really useful tool. The Gambit runtime also gives us a polling mechanism in the code to interrupt the code that's running at a safe point when the code is executing. So we can use that mechanism to interrupt the runtime and basically do the same thing as the CPU interrupts on your computer. So we use that system to propagate interrupts, and I'll get to that in a moment. Before maybe getting into that, I'd like to give maybe a quick overview of the system and the architecture of it so you can better appreciate what's happening later on. So you can see that the Scheme kernel is made out of the Gambit runtime system as well as the drivers that are also in Scheme. So this is all in Scheme, and this is executing a direct hardware. It has a direct hardware access to execute the commands on the hardware as well as yeah. You also see that there's a C kernel, and the C kernel has a bit of a supporting role in that it provides some standard library function that the Gambit runtime would expect in a normal environment, and it propagates interrupts from the hardware to the hardware. Interrupts are propagated from the hardware to the C kernel to the Gambit runtime. So the C kernel is a bit essential in that it for now it supports the Gambit runtime. And I know I talk about the interrupt system a lot. It's the most interesting part of the project because it is a very challenging system to implement because of garbage collection passes, and I'll get to that right now. So the first implementation of the interrupt system really was straightforward. So when we would catch a CPU interrupt, we would receive them in a C handler code or a little stub function, and we'd dispatch it to the scheme kernel with the interrupt system provided to us by the Gambit runtime. So the code you see on the screen is exactly how it worked, beside the send Gambit function. I'm not going to go into send Gambit int. I'm not going to go into that, but that's basically all that is required to send an interrupt to the Gambit runtime. And that worked well. At first, we implemented the keyboard driver so we could use the REPL right away. But we quickly ran into problems with more advanced usage. So when a garbage collection pass would occur, interrupts would be dropped because since Gambit uses a blocking garbage collection system, no scheme code is allowed to execute when a garbage collection pass is occurring. So interrupt signals would be lost if multiple interrupts would happen in a very short time. And we would start losing key presses, and reading from the disk would not work well. So we really had to rethink our design. And the most straightforward solution that would come to mind if you encounter this sort of problem is obviously buffering your interrupts. So that's exactly what we did. So we added a static in-memory buffer that can contain a limited amount of information, obviously, because it's a static buffer, but also of interrupts. So this is problematic in the sense that now, if you get big bursts of interrupts while long garbage collection passes are occurring, you're still going to have data loss. So in order to mitigate that problem once more, we made the following observation. So some interrupts can be treated later in the sense that they don't have to be handled right away, while other interrupts need to be handled as fast as possible, because if we don't, we're going to start losing data in that part of the interrupt system also. So for example, IDE or hard drive interrupts only act as signal and tell you that the disk is ready for receiving or sending data. So you can delay these interrupts until you're ready to really deal with them. And we call these interrupts flow control interrupts because we can control the flow of execution of these interrupts. And as a counterpoint, some interrupts, like the serial interrupts, are exactly the opposite. So these interrupts, you cannot control the flow of which they come in, because if you don't treat them as immediate as you can or as soon as possible, you're going to start losing data. So this is the case for the keyboard interrupts, for instance. You can't tell the user to stop sending key presses. That would be ridiculous. And the same thing with the serial connection. Sometimes you have hardware support to tell the sender to stop sending interrupts, but sometimes you don't. So in that case, you still have to you still have to support them to receive them as fast as possible. So with that observation, we can improve our system, because now we have a way to partition these interrupts in two classes and deal with them differently. So sorry, I switched over. There we go. This is the current design of the interrupt system. Flow control interrupts, because we now control their flow. We can be sure that we never have more than one that is pending, because we can just delay the processing until we're ready. So flow control interrupts are going into what we're going to have as a bit set of interrupts that need to be treated. And at the same time, flow uncontrolled interrupts are going to be placed in a static notification queue, just like before, because we really need to acknowledge them as soon as they come in, and then get the data we need, and then just send it to Scheme so Scheme can deal with it. So the notification pump thread that we saw earlier in the demonstration is the one that's going to receive these interrupts, read them from the queues or in the bit set, and dispatch them to the Scheme handler thread. So and then the drivers can just deal with it in the way that is appropriate for the interrupts received. So this design is not perfect. There are still some problems with it. Obviously, flow control interrupts are never lost, because we really control the flow at which they occur. And this is helpful because some IDE interrupts now, because they fall into that category, are never lost, and we never have data loss when we're reading from the disk, for instance. But on the other on the other side, flow uncontrolled interrupts may be lost during high bursts of interrupts. So if someone is really angrily typing at the keyboard while a big garbage collection pass occurs, you might start dropping key presses. And they still need to be buffered because since they need to be processed as fast as possible, we can't really do otherwise. And there are other approaches that we thought about to mitigate interrupt loss, or maybe outright remove it. So the first solution again that would come to mind is allocating bigger memory queues. But during the reception of an interrupt, your goal is to really finish your work as fast as possible, because that you're freezing out the whole system. So starting to deal with memory allocation is really inconvenient. It's slow, and you might not even have the memory required to do this allocation. So in that case, you're still going to lose data. You could also move the treatment of interrupts into C or assembly, because you can ensure that you don't have dynamic memory allocation and you're never going to be paused. But that would really go against what we're trying to achieve here, because we're trying to do the exact opposite. We're just trying to have everything in Scheme and not in C or assembly. And that's, if you start patching everything with C or assembly, you pretty much failed your goal of having a Scheme on bare metal, really. But the proper approach in our mind, and something we're working on right now, is to have a subset of the language, so in our case Scheme, that works without memory allocation. So it operates on a statically allocated memory area. And what would that achieve is that since this code will never trigger garbage collection passes, because it never requires memory besides what was already given to it, well, it could execute while a garbage collection pass is occurring, and that would be really useful to really deal with interrupts in a way that doesn't require put them in a queue and dealing with them later. We could just execute it right away, just basically like a C interrupt handle would do, so without having to rely on dynamic memory allocation, and just execute it as fast as possible. So now that we covered a bit the problems we encountered with the interrupt system, I'd like to talk about the role that the REPL played in our operating system. The REPL is really useful because in our system it can access every Scheme driver, and it has full or raw memory access if you want. So it as a consequence, it has full hardware access. So an important part of operating system development is tinkering with hardware. So of course, having full hardware access in a REPL facilitates driver development a lot. So with those tools, we really have what we need to start developing really quickly and experimenting with the hardware. And a big role that the REPL played is into debugging the system. So in an operating system, you're often dealing with peripherals that are obviously changing your state, and sometimes you're gonna have hard to reproduce event flow based bugs. And with the REPL, as soon as a bug occurs, you can start fixing it, as opposed to traditional operating system tools where if you notice this bug, then you have to implement something to catch it, and then you have to rebuild the system and then rerun it. And then after that, you have to recreate the faulty state or the sequence of events that led to this rare or weird occurring bug. So this is much more convenient if you can just start typing things right away. And this is actually something that happened quite a bit in our process of developing the system. For instance, the UART system had bugs where it would happen sometimes, but not always, or well, we had to do the correct sequence of events. But by just being able to interact with the REPL, with the UART driver within the REPL, sorry, we were able to find out what was the bug, and we could see the invalid states being set, and we could really quickly fix the bug. So the REPL allows you really to sometimes avoid these build cycles that are costly in time and really slowing your development. And since you can just execute test routines while the bugs are occurring, you can really explore what's happening. And another great feature that is given us by the REPL to do debugging is the symbolic debugging that the REPL can enable if your drivers are interpreted by the scheme runtime, for instance, or maybe compiled. I'd never tried the compiled debugging. maybe as a last point, as a last reason why the REPL is really useful, is that it really allows you to explore memory, interact with the hardware, really experiment and learn about how the hardware is behaving under certain conditions. If, for instance, your documentation is poor, or something happened and you're not sure it was supposed to happen, if you want to try to reproduce it, this is really a great interactive tool to verify that everything is running as expected. And I'd like to conclude now with maybe the bad parts of our design and the lessons we learned. So, of course, garbage collection comes at a price. It gives you a performance hit in the sense that when the garbage collection pass occurs, your whole system is frozen, and this is not great. So we have solutions to these issues, and in theory, they work. But we were still in the process of testing everything. And as of whether Scheme can be adapted to operating system development, this is definitely a yes in our mind. It brings powerful tool like the REPL, which is a great tool for OS development, tinkering with hardware. It's a really powerful idea that brings a lot of tools that are not typically found in traditional operating system development. So if you'd like to know more about the system, you can find the code on GitHub at the UDMDL team user or team, I'm not sure, and at the Mimosa repository, and the paper that is with this presentation. Details more on the usage of Scheme and how it played an important role, and how really we adapted it to do the things that it doesn't traditionally do. So I didn't talk about that much in this presentation, but there was some adaptation work that went into making Scheme effective to these tasks. Thank you for your attention.